I will now be presenting this work titled Displacement Monitoring of a Pedestrian Bridge using 3D digital image correlation. Starting with the background and objectives of the development which I'll be presenting. The motivation behind this work is developing structural monitoring systems in an urban context using computer vision techniques, and it's part of an effort to establish long-term setups that can assess the behavior of structures and identify changes in that behavior over time as a form of predictive maintenance. And since we're in urban scenarios, we want our systems to present minimal disruption to the structure and its surroundings. We want to avoid interfering with the structure itself, and we want to avoid setting up disruptive support structures for the vision systems as well. So the test setup, which will be presented here, consisted of a vision system that measures the deflection of a pedestrian bridge using 3D digital image correlation with cameras installed on an adjacent building by windows. Now we'll go over the setup of our test, so the components used in the test and their layout. On this image you can see the pedestrian bridge and the building beside it, and a schematic representation of where we installed the vision systems and where we exerted the load. So the 3D system was installed on two different floors and captured the bridge from above, whereas we had a 2D digital image correlation system as well on the ground floor parallel to the bridge and looking at it from the side. And the load was static and consisted of a group of 7 people standing near the region of interest, there where it says load on the schematic. The setup of the system was heavily conditioned by the layout of the structures themselves, especially by the locations of the windows on the face of the building which is facing the bridge. The 3D system was set up on the highest large windows available, with cameras at a distance of 4 meters on adjacent floors. The stereo angle was only 3 degrees, which is quite low for what's usually ideally practiced in DIC, but we were conditioned, like I said, by the locations of the windows. They were at a distance of 30 meters to the region of interest and captured about 3.5 meters of the length of the bridge. And then the 2D system was a camera 13 meters away from the region of interest, and it captured about 1.4 meters along the length of the bridge. And because of the trees which obstructed some of the bridge's view from the window, we could not point the camera perpendicularly to the surface, which forced us to implement a perspective correction algorithm. The 3D system consisted of 2 IP cameras suited for video surveillance with a resolution of 12 megapixel and a 75mm lens. So both cameras were connected to a common network as well as the computer which was used to control the image acquisition. As for the 2D system, it consisted of an industrial USB camera plugged into a laptop computer with a resolution of 4 megapixel and a 150mm lens. So as for the test itself, we started by acquiring images of a checkerboard pattern for calibration of the 3D system. We also acquired a single image of a calibration pattern pressed against the surface for the 2D system in order to correct perspective. Then we acquired reference images on all systems with no load applied, so no one on top of the bridge, and those are the images we can see here on the right for the 3D system. And then the load was applied, so the group of people which stood on top of the bridge was instructed to go onto the bridge, and so the loaded images were acquired. The image acquisition was independent on the 3D and 2D systems, and it was triggered manually on each of them by different people. And the synchronization was unreliable not only between the 3D and 2D systems, but in this case, within the two cameras of the 3D system, there was also a slight problem with synchronization, meaning that only static loads could be evaluated, since we could not guarantee that both cameras were acquiring an image at exactly the same time. As for the speckle pattern, we didn't need to prepare the surface of the bridge because the natural irregularities of the bridge, which you can also see on the images, served as a perfectly fine speckle pattern. Of course, we have no control over the dimensions of the speckles and so on, and we can't guarantee that these dimensions are the same all over the surface, but in our case it worked perfectly. So as for the processing of the 3D test, we started by calibrating the cameras using the Zhang method, and then we performed DIC using our own algorithm, which uses the discrete Fourier transform, and which has been the subject of a previous publication by our team. For the stereo matching, we used feature matching to get point matches between the images from both cameras, and then we found a projective transformation between them, which is a very good approximation since the surface of the bridge is flat. And then applying the transformation to one of the images, our work in stereo matching is made much easier because the images look nearly the same. And so at this point we performed DIC between the transformed images. And for the 2D test, as I said, we needed a calibration procedure. That was because we could not make it so that the camera was pointed in such a way that the sensor was parallel to the surface. And so we needed to correct perspective. So for that purpose we took an image of a checkerboard pattern pressed against the surface, and then we detected the checkerboard corners, and we computed a projective transformation that makes the pattern appear parallel to the image plane. So we're making these squares of the checkerboard pattern also look square in the image, and so we make the whole surface look flat. And so then we just apply this transformation to all the acquired images, and the surface against which the pattern was pressed will look flat. And like in the previous case, we used our own DIC algorithm using the discrete Fourier transform. And originally we intended to track only one point, but then we verified that we could make a field measurement along this span of length of the bridge that we captured. And now we'll look at the results for both tests. Here is the 2D test with the displacement magnitude represented as a field, and the direction of the displacement of each subset represented as well. The mean value of the displacement overall of the subsets was 3.1 millimeters. And here are the 3D test results. We can see the absolute displacement field over the region of interest, with a mean value over this whole area of 3.2 millimeters. And we can take away a few conclusions from these results. There's a good correspondence with the expected behavior in terms of displacement magnitude as well as displacement direction, and the 2D and 3D results are in agreement as well, with very similar mean values over the measured areas. The displacements of the subsets in the camera images under our setup were all quite small, and always under 3 pixels, which means a lower resolution system might not have been able to detect them using the same physical setup. And finally, we can see some spatial variation over different areas of the region of interest in the 3D test, but the field of view is relatively small, so we can't expect to see a very clear pattern. With shorter focal lengths on the camera lenses, we would be able to measure displacements on a longer section of the bridge, so maybe we would have seen a clearer pattern, but we would have lost resolution for displacement measurements. There are now some conclusions we can take. We have installed monitoring systems based on digital image correlation with a camera setup taking advantage of existing infrastructure without the need for the preparation of the surface with a speckle pattern, and the results obtained were consistent. And some further work, which in the meantime is under an advanced stage of development, includes demonstrators in less controlled environments with, for instance, natural loading caused by passing vehicles instead of a load controlled by us. Better synchronization of the stereo camera system in order to evaluate dynamic loads, and validation of our DIC method using other techniques such as sensors installed on the structure. And that's all from me. Thank you.